Hello, everyone, and welcome. We are delighted to have you here today to explore how to unlock design insight with QUGATE in pSeven Enterprise. How many simulation do you really need? We are honored to have three outstanding presenters here with us today. Let me introduce them one by one. So first, welcome to Kujtim Gashi. Kujtim is the CEO and founder of QUGATE and is bringing over 10 years of surrogate modeling experience to a practical platform built for simulation-heavy engineering teams. Hi, Kujtim.
Good morning, everyone.
And let me also give a warm introduction to Laurent Chec. Laurent Chec is General Director of pSeven, and he brings extensive experience in the world of design and simulation industry. And he has been pSeven Director for more than a decade.
Good morning, Leonore, and good morning, everyone.
And last but not least, let me introduce you, George Biryukov. George is application engineer at pSeven for more than 4 years now. And he also leads a training session for pSeven Enterprise platform, which he will showcase during this webinar. So welcome, everyone. And let me just give you a quick reminder before starting this webinar. All attendees will be muted, but you can submit your questions at any time in the Q&A session. So feel free to do so. And now let me hand over to Laurent to start this webinar.
Yep, thank you, Leonore. Let's start. I will just take a few minutes to introduce the company, our technology, and then we'll hand over to Kujtim for the presentation of QUGATE technology. So to start with, I'd like to say a few words about our origins. The company has been founded in 2010 after research activities within Airbus. And we are independent now since 2015, so more than 10 years. And we are headquartered in Toulouse, no surprise, because this is Airbus location. Aside of developing software, which is of course our core competency, we have expertise in a lot of engineering domains, disciplines, in mathematics, in data science, and we are in that business for many years, and we have a worldwide presence now with more than 100 of customers everywhere in the world. So we sell our technology directly or through a channel of resellers, essentially Europe and Asia. Our activity is concentrated on software development aimed at providing collaborative environment for engineering activities. We allow engineers to automate their simulation workflow, to do design exploration, but also we enable the knowledge capture and sharing at scale. And this is an emphasis that I will give in the rest of my presentation. Some references here. The logos are very famous and leading edge companies. The common aspect of all these companies is the fact that they are quite advanced in simulation methods, and we bring value essentially when companies are already quite advanced, and they need to get to the next level in terms of integration, in terms of multidisciplinary analysis and so on. The technology itself is totally agnostic to the industry or the discipline, and this is why you have so many logos in different industries. All these organizations face pretty much the same challenge, whether you are in automotive, aerospace, or chemistry. There is one thing which comes back again and again, and since decades actually, it's the shortage of experts. This is something which has been highlighted during a recent research in 2023. So McKinsey and NAFEMS, if you know that organization, quite well known in CAE and simulation, they have driven a survey and analysis of the market, and without surprise, among 176 companies they have contacted, 61% of them have mentioned the talent and skills shortage as #1 barrier for the massive or wider simulation adoption. So this is a critical thing in most industries, that the expert represents today a kind of bottleneck. So he has a great know-how in the disciplines, and of course the company benefits from this. But the number of experts in all industries is so small that there is a real bottleneck, which then induces different issues or challenges. So delayed iteration, so with the longer development cycle, the fact that that expert can certainly not do all the design exploration by himself. He can advise, but there is such a big amount of work that he cannot do this by himself. And that concentration of know-how and expertise can be extremely dangerous, of course, in the case of resignation, for example, or the guy is going to retirement, because as you can imagine, the experts are quite people who have many years of experience. So some of them are close to retirement, and when they leave, it's sometimes a disaster. And so we have to do something here. And this is what we try to address, the challenge we try to address with our software solution. If you try to fix just by increasing the headcount or bringing new experts, first of all, it's extremely difficult. But even if you are successful here, hiring just adds capacity linearly. It doesn't really change the picture. So this is where we, as software editor, have a responsibility and a card to play. The solution here is a software environment where the experts' know-how can really be shared at scale within the enterprise. So what we have done here is to develop a web-native low-code, no-code platform to facilitate the automation of engineering processes and their sharing at scale. It's 100% web-based, so you don't need to deploy any heavy client on the user machine. You can integrate any kind of workflow, any kind of process, CAD, CAE, data science, whatever. The platform is totally agnostic to the discipline. There is a very also efficient engine behind. So running the workflow can sometimes be extremely complex because you have multiple branches and conditional statements and these kind of things. Yeah? And on top of that, on a very heterogeneous IT environment. So the platform allows and copes with this, and allow again the experts to cope with that situation and then share his expertise at scale. Among the capabilities that you will find in the platform is, of course, an algorithm foundation. So machine learning, AI algorithms, as well as optimization, uncertainty quantification algorithms are available there. It's a low-code environment, meaning that people can build workflow easily just by using the mouse or very light scripts. Any kind of CAE application can be integrated, as I said, and we can transform workflows into web apps in order to share those complex workflows sometimes through a very simple user interface. The system is completely open, provided with a REST API, so that you can connect to other collaborative platforms. So the interoperability here is a key aspect. And it is even a system you can fully customize in multiple ways. This is definitely a server-client architecture, and it's cloud native. So cloud means that the architecture is ready for deployment on a cluster. However, the system can be deployed on-premise, so within the customer environment. So you don't need to deploy this in the internet or on a cloud provider like Amazon or Azure, yet you can do it, of course, if you want. So this concept of sharing expert know-how at scale is something extremely important here, and this is where the value comes from. So the paradigm here is build, scale, and value. So just with one methodology, so build and master by the expert, and here he will use, of course, this workflow approach to capture the knowledge and to organize all his discipline. With just this, let's say one expert methodology. Whoops, sorry. one expert methodology can be shared at scale with many other, let's say, citizen users. And the sharing can be done as is, as a shareable workflow, sometimes locked to prevent any alteration of the method by the end users, and sometimes it can be shared as a web application. We have a specific area of the software called Apps Hub, where it's a library of web apps, very easy to use. You can open them from, of course, your browser on your PC, but also from a smartphone or a tablet. And then you can access the workflow without managing its complexity. And then this can be shared within the organization with a lot of users and very different profiles. So people on production, people on the shop floor, people on test bench and test environment, even salespeople. Why not? Because sometimes they want to do, I don't know, trade-off analysis during a call for tender. So all of that is made possible thanks to a very nice architecture, and the creation of these web apps is totally automatic. The underlying technology is, as you can imagine, extremely advanced. So we provide a lot of algorithms here based on our first, let's say, expertise from the Airbus days. So we provide DOE technology, optimization technology, machine learning, and AI to build ROM or reduced model, surrogate models. We provide uncertainty quantification capability. And all of that organized using some block concept. So you have seen on the previous slides the look and feel. So my colleague George will give you the live demo, so we'll see all of that in details. But the concept is to have a representation of the engineer's process as a block diagram representation, very, very convenient, and low code or no code. So all these capabilities and algorithms are actually provided within a single and unified block called design space exploration, or another one which is related to the learning process for machine learning. So this is a model builder. All of that is quite complex. There is a lot of mathematics inside, and to overcome the issue of tuning these algorithms, even selecting these algorithms can sometimes be challenging. We provide also a unique technology called smart selection, which allow engineers to automatically to let the software select the algorithm, the best algorithms for a given context, conditioning of the problem, and to tune it automatically. We don't enforce this technology neither. So if you want to use external technology, external algorithms, for example, this is absolutely doable. And this is the topic of today. So today we have QUGATE colleagues presenting their technology and how they integrate within the pSeven enterprise environment. So you can do that with QUGATE technology. You can do that with other open source software if you want. So again, this is how we provide a very nimble and easy to customize environment. So the technology itself, and speaking about QUGATE, these algorithms and their technology is actually available from a new let's say part of our website. Probably you know that our website is pSeven.io, and there is a subdomain called marketplace.pSeven.io that you can connect to, and this is where you will find third-party technology, including QUGATE technology. So you can, as a user of the pSeven Enterprise platform, you can go there, connect with your credentials, and then grab the application that you need and seamlessly integrate it into your block library, which represents all the methods, the wrapping methods that we offer in pSeven Enterprise to build the workflow. So George will also present this. So this is the end of my introduction, and now I will hand over to Kujtim.
Good. Can you all see my screen? Like this. Let me share the entire screen. Perfect. let's do it like this. Yeah, thanks, Laurent. So I'm part of QUGATE. So QUGATE is a Dutch company. We are based in the Netherlands, and what Laurent just showed you is basically the platform, the workflow environment, and the marketplace with the connectors. And what I want to do in the next 20 minutes is to show you what changes inside the workflow when you drop the QUGATE blocks in. And one sentence as a frame is that most simulation teams get the insight at the end of their campaign, and our blocks let you get it like while the campaign is still running. So you as a team or you as a user can basically see like when the model has seen enough, and that's basically what I would like to show with a public available data set. Before I start, I would like to mention that our work on surrogate models is co-funded by the European Union, Open Zuid, and the province Noord-Brabant in the Netherlands. So let me get on it. A quick context, what we are working with. So we have the Drive RML, which is a public CFD data set, which is like on automotive aerodynamics. So we have 484 runs in here on a parametric vehicle with 60 geometrical parameters, 5 output parameters, such as the drag, the lift coefficients, and a side force coefficient. And the data is validated against a forward wind tunnel, and each run is basically roughly 40 hours on an HPC with around 1500 CPU cores in there. It's public, you can download it basically tonight. I want to be clear like why we're using this data set. So the team that built it did exactly the right thing. This is the gold standard, and the reason why it's so interesting and also to see like how it really fits within the pSeven workflow is that with this data set we can show like what the ground truth is. So we know what will happen after 484 simulation runs. So we can ask, at what point in the campaign did the engineer already have enough to act? And the honest answer turned out to be a surprise to us as well. So the issue that we keep seeing is that engineering teams running campaigns are seeing the results only at the end. And the problem isn't that surrogate modeling doesn't exist. It is depending on the field that you're in. It can be quite a mature field. Most engineers have heard about it. So either with the term surrogate modeling, meta modeling, predictive modeling. The problem is that when the trust arrives. So that's really the thing is like, okay, when can I trust my surrogate model or my meta model in such a way that I can base my decisions on it? And the typical workflow is you plan a design of experiment and you have a sample budget. So let's say 200 runs. You launch the campaign, you wait, you somewhere near the end, you have built your surrogate, look at the fit, run some sensitivity, draw conclusions. But then by that point, your HPC budget is gone, your timeline is gone, and if the conclusions suggest that you should have explored, let's say, a different region of your design space, then that becomes a separate project. So you will need to redo things again. What we have seen also is that there are cases where optimizations, for example, are done, and it's more on a hit or miss. So, for example, where engineers run an optimization to have a different kind of geometry or more different kind of settings, and it can be either locally or globally. But then after 40 runs, it turns out that the optimized geometry is not feasible. And it's either because the geometry is like not manufacturable or it's too expensive. So you have to run the optimization again for a different set point and then hope that this time the results give you satisfying outcomes. And this by itself and can also like push your timeline behind days, weeks, if not months. The issue itself isn't building the surrogate model, it's knowing like when you can trust it. And the standard approach is trust comes when the campaign ends. And we think the trust should come like way earlier when the surrogate model stops changing. So you can really act much earlier on that. So a quick technical detour, and I'll keep this one quite short. So standard surrogate modeling already fixes the model structure up front. So you have a fixed model structure, and then based on that, you fit your data. If the model structure that you've defined is too simple, you're basically underfitting your behavior. And if it's too complex, you need a lot of data to identify all your terms in the model. And we do this basically on the adaptive side of the surrogate modeling. So what we use is a polynomial chaos expansion for those who are more into the details. We have orthogonal polynomials, but in essence, what we do is we evaluate if a parameter has a meaningful contribution. So let's say a parameter is explaining your drag coefficient, if explaining your other output of interest. If that parameter is being important, we will include additional terms in there to make sure that the behavior is captured. If, for example, parameters, we see that they do not explain much of your output, those terms and those parameters can basically be pruned. So in this way, you get the smallest feasible surrogate modeling model that you can have that explain the result, but also in such a way that it doesn't overfit. And one thing I want to mention, and I think that's also quite powerful here with the combination between QGATE and pSeven. pSeven basically can help you out figure where you should put your next design point, and we as QGATE can help you to figure out okay, when has the surrogate model seen enough to basically be able to make decisions available. So concretely, what we have in the marketplace today are the 4 blocks. Each block builds our adaptive polynomial chaos expansion surrogates internally and exposes only one engineering question at a time. So for the sensitivity analysis, basically what it tells you is already early on, you can determine which parameters are having a big influence on your output of interest. So in this case, we see the parameters and their relative contributions with respect to the drag coefficient. It's basically done with sub-ball indices, which is a nice way of showing how effective or how important the parameter is, meaning a sub-ball indices of 0.5 gives you 50% of your variance is due to that one specific parameter. And what you already can see here is, in this case, that you have a couple of parameters that do play an important role, but a lot of them don't. So then it's up to you as an engineer to basically go and act on this insight, what do we want to do here. Another thing is where with a number of samples, so you've run your model, you can capture the surrogate model behavior. And instead of doing a expensive, let's say Monte Carlo on your high fidelity model, you can basically do that with the surrogate model. So you capture the behavior, and in this way you can estimate distributions quite accurately. You can check what the percentile is of your interest, say, let's say the 5 or 95%. You can see okay, what kind of reliability or confidence do I need on this model to be more accurate or to be able to act upon. So you immediately get the feeling of how your distribution looks like. The reverse search optimization basically inverts the question. So you as an engineer can basically have a question as in, I would like to have my drag coefficient below 0.25 or below a different kind of value. Show me the design space that basically gives me those results. So where do the geometries that give me this result live? And in this way, you can explore your design space quite efficiently with the basic number of runs in there. We have as well the Pareto front. So in this case, we have mapped on the x-axis the drag coefficient, and on the y-axis, the lift coefficient. So these are two competing variables. So on one hand, you would like to have your drag coefficient as low as possible. For a car, that means like a lower fuel consumption, but you also want to have a higher negative increase in your lift coefficient, because then the car is stable on the road. And there is a trade-off to be made. If you want to have a low drag, then you basically have a point that has like a suboptimal or like a less optimal lift. But if you have like a large lift, then basically your point is more, you have a more or at least a less aerodynamic car. So here the engineer can basically figure out, like, okay, what is this Pareto front? And if you click on each of those points, you basically get like, how do I need to choose my parameters to be able to match that car that I'm interested in. So each of the surrogate engines, each of the blocks share one engine, and they are all one self-containing block. So you basically drag them, connect them, run them, and then analyze the results. And then based on that, you can make your decisions much earlier. This is the chart that I would like to show, and that's also like how that changed like how we think about the number of samples that we need, like the sample budget. So on the x-axis, we have the number of simulations or on runs. And on the y-axis, we basically have the Q squared, which is a leave one out cross-validation. And similar to the R squared, if it's 1, it's perfect. It captures the behavior. If it's 0, it's quite bad. So 2 things to look at. So we are basically the red line. So that's basically us. So already at 32 data points, which is twice the number of the input parameters, the Q squared is already at 0.98. At 47 samples, we crossed the 0.99 barrier, and from there on, like throughout the entire range, we basically stay there. That means that with 437 additional runs of CFD runs, roughly 17,000 additional HPC hours, your accuracy gain is essentially hasn't improved. The model has already settled. Second, what I want to show is we have this band, this gray band, and that's basically the range of accuracies that you would get from standard surrogate methods. So with the same data, the same split. So even at 484 samples, it doesn't cross the 0.99. And we already have done it here. And this is for the drag coefficient. But the part here is, at least like what I want you to take home as a message, is that this curve isn't something you get like after the fact. You can build it while you're simulating. So you can start with your with an initial batch, and then based on that, you can increase until you basically are content with the amount of the predictive power of your surrogate model. And on this data set, the answer is like 47. On yours, it might be 30, it might be 80. But the point is, you'll know like while there is still like budget left to redirect. So here we have the graph for the drag coefficient, and we can do the same thing for a much more difficult parameter to fit, which is the side force coefficient. And what we have in there is we all start a bit lower, so at 0.8. We do increase quite a bit to 0.93. It's quite stable with a slight increase. But if we look at the methods, the other standard surrogate methods that you could have had, is that it actually drops to a much lower value than what we had with the lower set. So there is like much to be gained by using the right tool for the right simulations. Q squared is one thing, so really the predictive power, but engineers are also interested on sensitivity ranking. So which knobs do I need to turn? So imagine if you have like 16 knobs to turn on, it isn't feasible to turn all 16 at once or one at a time. So you really want to have, okay, what are the top 3 or the top 5 knobs that I need to turn on? What we have done here is we have plotted those like knobs, those parameters, as a function of the sample size. So again, on the x-axis, we have the sample size, And on the y-axis, we have like the main sensitivity indices, like how much of the variance does each parameter explain. You're looking at 16 lines, and the horizontal dashed lines are basically like what you would get at the end. And there are three things to notice. The top driver is the vehicle ride height, which is about like 0.5 in indices, meaning like 53% of all your drag variance comes from this parameter. And that's an actionable insight. That's also something you get like really early on. Second is, and that's the whole point of this talk, those lines are actually quite flat. So from, let's say, 47 samples onwards, the ranking doesn't change that much. And the decision you act on is focusing on the top three parameters, which is the ride height, the rear overhang, and the vehicle pitch. The other ones you could already freeze to values that make sense within your own requirements. So the decision could come on week 1 and not month 4. Point 3 is that the bottom parameters of low importance, in this case 12, are identified at already 32 and 47 samples onwards. So you already can ask the question, do I want to dive deeper into the parameters that actually matter more in this case? So the way we see QGATE being used in practice inside pSeven is a slightly different rhythm than most teams are used to. So we start with a minimum number of samples, which is twice your number of input parameters. Based on that, you can generate it with Sobol, Latin Hypercube in pSeven and run it. You build surrogate, look at the Q-squared, the sensitivities, the uncertainty bands, and decide, do I have my answer? Do I want more runs, or do I want to reshape the design space, maybe drop a parameter that's clearly insignificant, or multiple parameters, or maybe narrow the range based on like how the surrogate is behaving. Based on that, you can add like batches of, let's say, 5 additional runs and repeat the cycle. So you don't have to wait until you have finished like all the 200 runs, but already can stop maybe earlier on at 60 or at a different value. So it becomes a feedback loop, and the same workflow becomes like reusable, as Laurent already mentioned. So once you've built it with one project, your team can run it for the next one as well. So 3 things that change for an engineering team is 1, your decisions stop being gated on campaign completion. So the conversation with your design lead happens already at week 1 and not month 4. 2 is that your CFD spend or FEM spend lines up with the type of problem that you actually have. So instead of budgeting based on a guess or an educated guess at the start, you can basically like increase it while you go. And what we saw with the Drive RML is that you can, or in this case, we got like quite decent results with like 10 to 15 times the lower samples than like the full samples that we got or that we had to our disposal. So we're not promising like 15 times the reduction, but at least like a significant one compared to what is out there with the standard surrogate techniques. And the third one, and that's also the proof from the previous slide, is it's just not that we converge faster, so with lower samples, we also settle higher for a higher Q-squared. So the predictive power of the surrogate models on our side are much higher than what you would have on the other ones. So even if sample budget isn't your constraint, the model that you ship is like way more reliable. So George, over to you for the demo.
Thank you, Kujtim. Let me share my screen. So yeah, thank you for this interesting speech. And now I would like to take my part. And of course, we discussed that how to generate the surrogate models, what budget should be, and so on. But an important thing to ask is how to generate the data set efficiently, and how to allow simple engineers to prepare the data sets for the model training. To begin with, let me remind you a little bit the problem we are working with. So we are looking at the CFD analysis of a vehicle where we have identified 16 geometry parameters that are presented on the slide here. So the parameters as length, height, and some others. To be able to prepare the mesh efficiently for all those designed variants, we are working with the project in ANSA that allows us to prepare mesh by doing the mesh morphing based on these geometry parameters. Below here on the image, you see the simulation workflow that is performed each time for each new design point. So we start here on the left with the mesh generated in ANSA. So we change the geometry parameters, we modify the mesh, and this mesh becomes the input for this big cycle here, which is performed in OpenFOAM, which is used as a CFD solver to produce the results. And well, I don't want to spend a lot of time here on the technical details, but as you can see here on the slide, so the project is OpenFOAM that was used, was quite complex with some changes to the default solver to increase the robustness and to output more meaningful results. And also, by the way, this project in OpenFOAM, it wasn't constructed in a way that it can be efficiently parallelized on the HPC resources. But yeah, anyway, starting from ANSA with generating the mesh, we provide the mesh to OpenFOAM project, where we run the simulation, and the results of our simulation, well, there are many of them, such as pressure fields, some different distributions, and also the force coefficients Kujtim mentioned in his speech. So all of that is done using some custom post-processing in Python, Purview, and some other tools. So the outputs we will take a look at in our workflow. Just for simplicity, will be the lift and the drag coefficients. So the lift coefficient is the force acting in Z direction here, and the drag coefficient is the force in the X direction. So now let's switch to the platform itself. So this is where we are. So for this project, what we did, we prepared several workflows, and the first one that I want to share with you is called simulation. So let me open it. And this is how the workflow actually will look like to automate the process presented on the previous slide. So we start with 16 geometry inputs, which we provide here at the start of the workflow. So you can see all of them with some default value assigned to each one. And then we provide all those inputs to the first block in the toolchain, so to the ANSA block. And to configure the ANSA block, what was done is we can open its interface. And here we've provided the ANSA project, and the block automatically extracted the design variables. So again, all those 16s. And we also select how exactly we want to export the mesh. So in this case, we use the OpenFOAM native format, polymesh, and we select all of our design variables to be the inputs of our block. So once we did this, we can close the interface, and we see that the inputs are actually connected through the links to our input port here. And the output, which is the polymesh format of the mesh, is pushed to the second block through this link here to the program block. So how we use the program block here now is we use it to start the simulation in OpenFOAM. So as OpenFOAM is a tool that supports batch execution, so we can provide the command line like this to our block, and the block itself, it will take all the needed inputs. So it will take the OpenFOAM project. It will also take the mesh file, which comes through this link from the previous block. It will run the simulation, and it will output multiple output files. And then in our line, we have a text block, which we used to actually read one of the output files provided by OpenFOAM to output those force coefficients as the outputs. So this block, in an interactive manner, it reads a new output file, which is provided by OpenFOAM. It knows where is the location of the exact force coefficient, and it maps it to a corresponding output variable. And this is what is outputted here as a result of our workflow. So we can see all the inputs, and here are our outputs, so 5 different force coefficients. So after preparing this workflow, we built a second one, because this one can be used to generate to evaluate new design points one by one by modifying the geometry parameters. But we also have another workflow here, where we actually use the design space exploration block, which will drive our simulation workflow to generate the dataset. So how does it work? The first step was to configure the design space exploration block here. So this is its interface. So here we provide the variables, we provide the boundaries for each of them in which we can operate. We also specify the responses we want to analyze. We specify the type of this response. So in our case here, we just want to evaluate all of them. And the technique proposed automatically by the block using smart selection mechanism is the Lighten hypercube sampling. We also see here the default budget proposed by the block. So for this number of inputs, it's 320. And with this, we finished configuring this block. And actually, the exploration budget in this case becomes the input variable for our block, which is connected here to the input, which we can later change if we want. So after we finished configuring the block, we now create the connection with our simulation block here, because what this block here is, it's actually the reference to the workflow which we saw just before here. So dynamic link, it means that all the changes we make in this child workflow are reflected in our DOE workflow. So once we've added this, we need to loop the cycle. So we've created the link. I can show you them to you. So basically, our design space exploration block now has multiple outputs that are the geometry parameters. So these are the design points the block proposes to evaluate, and all of them are connected through this different multicolor links to the inputs of the simulation workflow. And in the similar manner, we see the link in a different direction. So once the design parameters are received, they're being evaluated by our simulation workflow, and the results are pushed back to the design space exploration here. So if you will see the link, all those force coefficients are returned back to the design space exploration block. So that's why you see the blue links here. It means that this is a closed cycle, and the simulation workflow will be evaluated as many times as the design space exploration block wants to. So once the design space exploration block used all of its available budget, it will output different parameters. So it will output all the evaluated points one by one, but it will also construct one big table, which is actually the data set with all the designs that we can later use to build some predictive models and to make some decisions based on it. So this is the workflow, and I want to highlight that the existence of this workflow is mandatory if you want to generate the data sets efficiently with the variable budget you have. But now, once we've constructed with this workflow, we can bring into the picture the QGate blocks to make some decisions based on this data set. So now several words about our marketplace and how actually to get those blocks. So here you can see the page of the marketplace. It's available to everyone. The only thing you need to do is sign in if you already have an account, or register. The register is free of charge, so we don't need to do anything. And once you've authenticated, you can get the blocks from this marketplace. So let's find one of the QGate blocks, for example, the Pareto Frontier block. So we can open it. We can select the version that we want to get. Currently, there is only the first version that exists. We can click here on download. We can select. We need to select our pSeven Enterprise version, and we can click on the download here. So the website will propose us to download the archive with the block. So I will save it somewhere. And once it is downloaded, I can go back into the platform. I can put the archive into the platform. I can uncompress it, so unzip. And you see that the new block is here in our storage. And now the admin of the deployment can put this block into the common library here, so that it is available to everyone to be used in their workflows. So now, as a simple user, I can go back to my workflow. I can find the block that I need, and I can now drag and drop into my workflow, and now it appears in the workflow library. So now let me show you, just to save some time, already configured workflow with all the 4 QGate blocks available. So the most interesting part is that those blocks are compatible, fully compatible with the design space exploration block. It means that the only link we need to create here is the output of all designs table to the design table input of the QGate block. So we need to provide the data set. We also need to provide the names of, here, for example, for Pareto Frontier, the names of input and output columns. So in this case, these are the 16 geometry parameters and 2 output columns, so the drag and lift coefficients. And for what each of this block does, it provides a friendly report that any user can analyze. So the last thing to configure the blocks is the path to the report. So you can see that here, each of my blocks, it says a report under a custom name, right? And this is all you need to do to set up those blocks. And now let's take a look at how those reports look like. So we can go into the DOE workflow, we can go into the runs, and here I have several runs with different budgets. So let's first study the one with 47 points. So you can see that, for example, here 47 iterations of the simulation were made, and once the cycle was finished, we executed each of the QGate blocks. So here you can see the folder created for each of the run, which we can analyze later. But the interesting part for us is located here at the bottom. So 4 different reports, which we can open. So for example, the Pareto frontier, also the reverse search optimization, the sensitivity analysis, and the uncertainty quantification. So this is how the Pareto frontier looks like. So you can see that the report is interactive. You can select different points that you want to learn more. You can also see the optimum curve here. For the predictive modeling of the reverse search, this is the report you see. So in advance, we provided the ranges for the outputs we wanted to analyze. And here, as an answer, we see what ranges of the inputs provide those outputs. Here is the sensitivity analysis report. So here you already have some insights provided by the report. So what parameters have the highest influence, what parameters are safe to fix. You also have the exact value solvable indexes if you want to analyze them. And you see the cumulative explained variance report. So how much variance is explained by each of the parameters. And the last one is the uncertainty quantification. So as Kujtim said before, so we can analyze different percentiles to build more trust into our model. So we performed the same thing for different budgets. So for example, for 70, we had another run, and the same was done for 103 points. And for each of them, we generated a new report. And indeed, we analyzed that at some point, the results for sensitivity analysis were not changing. And this is where we could have declared that we can fix our simulation budget. And the simplicity of using this workflow is actually the exploration budget. It needs to be signed in only once. Here, for example, if 47 is not enough, we can use 50, 60, and so on until the results change. So this was a quick demo of how those QUGATE blocks can be used inside the pSeven Enterprise platform. And now to conclude our webinar, I will pass the ball to Laurent and Kujtim. They have something to share with you. So thank you.
Thank you, George. I'm going to share my screen. I think we'll let Kujtim comment on that one.
Yeah, definitely. So for each webinar attendee, we do have a 30-day trial, so a free trial. So if you're interested, you can mail us the webinar voucher code, like pSeven QUGATE, send it towards support@qugate.nl. Within 24 hours, we can activate your license, help you out to load your data, book a one-to-one appointment. And I think within 30 minutes, we can have your first surrogate model fitted together. That's about what we can offer to you.
Thank you, Kujtim. And on the pSeven side of things, we offer pretty much a similar process if you are interested in our technology. So we offer a kind of evaluation protocol in 4 steps, actually. First one being an identification of a critical process where you think you can get the most value upfront, at least. We identify the owners. We define some specific use case to represent these critical processes, and also the success criteria. So this is step number 1. Then step number 2 is the proof of the value. 60 days, free licenses delivered, kickoff meeting with a training session. We review the use case, and on a weekly basis, you are in touch with our experts to review the progress and to make sure that you are integrating the use cases and see hopefully the value. Step number 3 is pure return on investment review. So we make sure that we bring that value, that you have the sufficiently soon break even when you invest in our technology. And of course, this is where you can take your decision whether you want to deploy or not. And step number 4 is the deployment phase. This is a full license deployment. We of course assist in the deployment phase, whether it's for the deployment itself of the technology on a cluster, and of course the ramp up of the users and continuous improvement of the workflows that you want to integrate. So all of that is offered free of charge, and we would be delighted, of course, to engage into this process. I think it's time for Q&A now, so I will hand over to Leonor.
Yes, thanks everyone for this great, insightful webinar. So we have a few minutes left to answer your questions, so feel free to drop in the menu all your questions. I will bring everyone back. Yes, so the first question goes to QUGATE, I guess. So what is the maximum number of parameters and outputs the QUGATE blocks can handle?
Yeah, that's a good question. We don't really have a maximum number on what the software can handle. It's only like how much simulations you would like to have run. So up until now, we have seen that even with 25, we are able to reduce the number of runs quite a bit. But it depends on your model. So if you have a more interactive model with parameters, you will need more runs. But in general, if you have like more than 30, I think it would make sense to first evaluate like what kind of budget you have and maybe split it into 2 different runs. But on our side, there is no limit.
Thanks. And where do the QUGATE blocks struggle or require caution?
So you need to be a bit more cautious on really sharp discontinuities. So like phase changes, buckling, regime changes. If you have like high dimensional input, so for example, what we have now with 16 parameters, but you only have like, let's say 10 runs, then it's going to be like really difficult. Other than that, only if it's like really chaotic or highly stochastic, the blocks will struggle. As long as it's not that, then QUGATE will manage quite well to have a circuit model.
Okay. Another one, how does QUGATE help avoid local optima in design exploration?
Yeah, so what we do is we generate a surrogate model of your limited amount of data. And to make sure that we don't end up in a local optima, we don't use a gradient descent. For example, what happens on a costly simulator, we evaluate the surrogate model like really globally. Like we use like millions of data points to figure out like, okay, what are the regions of interest, and then based on that we have it like from a local point of view. So that's how we make sure not to have a local optima, but explore the entire high dimensional space.
Thanks. And another one goes to pSeven. So where does pSeven run OpenFOAM?
Yeah, thank you for that question. Maybe I can take over the screen just to comment on this. So here, indeed, we used the program block to run OpenFOAM. So by default, this block runs on the resources of the Kubernetes cluster where pSeven Enterprise itself is hosted. So this is possible if you have an environment prepared with OpenFOAM for Kubernetes. Another option is to run it on one of the Windows node that you can attach to the deployment if you have OpenFOAM there. And maybe the last option, and it's partially related to what I've mentioned in the beginning. So basically here, well, I don't have this block on this deployment, but basically in our marketplace, We have several blocks that allow to run on HPC clusters, so such as Slurm, or just SSH block. And in this case, you can benefit from your HPC cluster that you already use. And indeed, this can be more efficient in this use case, as the project for OpenFOAM was already prepared to be run in parallel mode.
And maybe we have time for one last question. What is required to integrate QGate blocks into an existing workflow?
Yeah, thank you for that question. So basically, you already saw how to set up the blocks. The only requirement after you download the blocks from the marketplace is to activate the license for them. So the license is node locked, so it means that it runs on one of the extension nodes you have attached to your deployment. So to issue the license, you can contact QGate, and then the last step would be just to create an environment to put the license file on the node where you want to execute them, and to create an environment variable that will point to the license file, and then the blocks will automatically find the license and so on. So probably this is the only thing that is required from you. Sorry.
So thanks everyone. So if you have any other question, you can feel free to write to us, and we hope to hear from you very soon. And so thanks.
Thank you, everyone. Thank you, Leonor, and speak to you soon.
Thank you, everyone.
Bye-bye.
Bye-bye.
Bye-bye.